Okay, so today we are going to be focused on mechanics questions, and in particular, we're going to be focusing on simple harmonic motion and centripetal acceleration. So these are the two topics we said we would focus on last week. So I have a few questions prepared that came up in previous years. So I'll just share my screen with you. Okay. So I'll just get set up. Okay. So today, the first question we are going to be doing is based on centripetal acceleration, centripetal velocity, and so on. So here is the question. This was 2009, question 6. I'll write that up here just so you know for your own records. 2009, question 6. Okay. The first part of the question was very simple. It just states Newton's laws, plural, of motion. So you should know by now that there's 3 laws of motion. They aren't too bad, but you really just have to learn them off. So the first law of motion. So we'll just summarize them down a bit, okay? So the main points of it are that a body will remain at rest or constant velocity unless acted on by an external force. Okay, so hopefully that's something you've heard by now in your physics class. A body will remain at rest or at a constant velocity unless acted on by an external force. Okay, so that was our first law of motion. That just means that anything moving will stay moving at the same speed or velocity, or will stay still if it already is still, unless there's a force acted upon it, an external force acted upon it. Okay, so that one's straightforward. Second one states that the force, well, okay, we'll say that the rate of change of momentum of an object is proportional to the force acting upon it. Okay, and there's a small bit because momentum is a vector and acts in the same direction. as the force. Okay, so that sounds like a lot, but it's not really. The rate of change of momentum of an object is proportional to the force acting upon it and acts in the direction of the force. Break it down like that. Now, there's also an easy way you could say that, okay? You could actually just, you could really just say it using a formula, okay? So you've surely seen this formula by now. Force is equal to, well, is equal to mass times velocity minus the mass times the initial velocity all over time. And it should be a proportional sign. So the force proportional to this is the final momentum. Mass times the final velocity is the final momentum. Mass times the initial velocity is the initial momentum. The final velocity minus the initial, the final momentum minus the initial momentum is going to be a change in momentum. So that will give you. And if you divide the change in something by the time, we're getting the rate of change. So we're getting the rate of change of momentum here. So the force is directly proportional to the rate of change of momentum. Okay. So you could technically just write down this. Okay. So that they are the same thing. And of course, but I would mention acts in the direction of the force that I'll destroy into. Okay, so if you were stuck, go for your formulas. The third one says, is probably the most well-known in Newton's laws. It states that every action and reaction are equal, but opposite. Okay, every action and reaction are equal, but opposite. Also, you might have heard this as, it's not always say worded that way. You might have heard it so that if something like, if body A acts on body B, then body B acts back upon body A with equal but opposite force. Okay? Or if an object A exerts a force on object B, and object B exerts an equal and opposite force on object A. Opposite just means opposite direction. So if you had, let's say, just A, some block of something colliding with B, what's going to happen is once A hits B, B is going to exert an opposite force, which means opposite direction, on A, and it's going to be with equal magnitude. That's what equal means. Okay, so if A exerts a 5 Newton force that way, B is going to exert a 5 Newton force that way. Okay, so those are your 3 laws of motion. Now, next part of the question. Show that F is equal to ma is a special case of Newton's second law. So basically what they're asking for here is for you to derive Newton's second law. So this is Newton's second law. Okay, and from this, you can actually derive F is equal to ma. So F is equal to mass by acceleration. What you want to do is go from this to F is equal to ma. So this derivation is just something you have to learn off. So it starts like this. The force, we state Newton's second law, which is the force proportional to the change in momentum all over the time taken. Start off with that, okay? Now, what you can do is, okay, we start with this. I'm gonna put a little, it says question 2 here. I'm gonna put a little, say, bracket here. A is equal to V minus U over T. Okay, so we're starting with this. And I'm going to say that we know acceleration is equal to the final velocity minus the initial velocity all over time. Okay, we know that. If you get the final speed of something and take away its initial speed, you get the change in speed. And if you divide it by time, you get the acceleration. So v minus u over t, v minus u over t. So we're going to sub a in for v minus u over t. We're going to be left with f is proportional to m times a. Okay, so we're going to be left with. Now, we want to get rid of this proportional symbol. Okay, we need an equals. We want f is equal to ma. So how we do is we say 1 Newton is equal to 1 kg times 1 meter per second v squared. Okay, so if we did this, we could introduce a constant k. As long as that k is 1, we should get 1 Newton here. So 1 Newton is equal to 1 by 1 kg by 1 meters per second squared. If we make that constant into a 1, we don't have to think about it. Okay, so what we're going to end up with is f equal to ma, where k is equal to 1. I guess that's why you get rid of the proportion symbol. You make it into a constant, put in your equals, and let that constant equal to 1. So f is equal to m times a. And that's that derivation. It's a nice quick one. Now, okay, we'll keep going. So this part of the question says, the skateboarder with a total mass of 70 kg starts from rest at the top of a ramp and accelerates down. So mass of 70 kg. Starts at the top of the ramp, accelerates down. Rest, look at that. Top ramp accelerates down. Ramp is 25 meters long, angle of 20 degrees through horizontal. It's here. Skateboarder has a velocity of 12.2 at the bottom, so down here. Okay, so first question. So let's go through again. The man was up here on his skateboard, started at rest, and he went down the ramp. The angle was 20 degrees, the ramp was 25 meters long. At the bottom, his velocity was 12.2. First question, calculate the average acceleration of the skateboarder on the ramp. Okay, so we need to get his acceleration while he's on the ramp. So how we do this is we need to work out A. Okay, so if we think about our formulas, we have our equations of motion. We have V is equal to U plus AT. We have S is equal to UT plus 1/2 AT squared. And we also have V squared to U squared plus 2AS. Okay, so we're looking for A. So these are the truths is see what you have and then see what formula fits. So A, we're looking for, so we could use any one of them to find A. Now, what else are we given in the question? We're told he starts from rest. So we know U is equal to 0 meters per second. We're told that the ramp is 25 meters long. So S, displacement is going to be 25 meters. We're told his velocity at the bottom of the ramp, so down here, V is 12.2 meters per second. And do we know anything else? I don't think so. So we have U, S, and D, and we're looking for A. So we can't choose the first one because we don't have A and we don't have T. We can only pick a formula where we only have one unknown. So we can't choose this one because we have two unknowns, A and T. S, we have. U, we have. T, we don't. T, we don't. A, we don't. So this one has two unknowns as well, so we can't use it. So this one must be our guy. We have V, we have U, we have S. All we need is A. So there's only one variable in this equation, so it can be solved. So V squared is equal to U squared plus 2AS. So V is 12.2 V squared. U is the initial velocity. Because he was at rest, it's just going to be 0 V squared. 2 multiplied by A multiplied by S is 25. Okay, so what you're going to end up with, let me get my calculator. 12.2 to be squared gives you 148.84. And that's equal to 0 is just 0. 2 times 25 is 50, so 50A. Okay, so that means if you bring A on its own, bring your 50 underneath, you're going to have 148.84 divided by 50. 148.84 divided by 50. And that gives you an answer of 2.98 meters per second squared. Okay, so that's the first question done. We were asked to find out his average acceleration as he traveled down the ramp. We just use V squared is equal to U squared plus 2AS and fill in what we know. Next part. Calculate the component of the skater's weight or of the skateboarder's weight that is parallel to the ramp. So this is the ramp. Parallel be this direction. Okay. And let's say if the skater is here, his weight will be acting down. Weight always acts down. So this would be parallel and this would be perpendicular components. Okay. So what we're trying to do is we're trying to work out, we know that this is 70 kg. That's his mass. So I'm going to redraw it here for you. So we have our man up on a skateboard. He is on a ramp. The ramp is a 20-degree slope. Now we're told that his weight, well, we're told that his mass is 70 kg. So mass is 70 kg. That means his weight is equal to mass times gravity, which is 70 times 9.8. That gives you 686 newtons. Okay, so this guy's weight is 686 newtons downwards. Okay, now what we're asked is how much of this weight can be divided into a parallel component to the ramp. So we're trying to work out this component. Okay, so that would be the perpendicular. This is the parallel. Now, if we make this into a triangle, so now if this is 20 and this is 90 degrees, that means 20 and 90 is 110. This would have to be 70 degrees, okay? So we're trying to work out if this is our, let's say, a triangle, this line. I'll try and get some color to emphasize it. So this red line here, this red line here, and this red line here. That's our triangle, okay? So 20, 90, 70. We know the length of this one is 68, or sorry, 686. We don't know this guy. We're looking for him, and we don't know this guy. Down here, we're looking for him. So think your triangle. Opposite the 90 is the hypotenuse. Opposite the angle, okay, is the opposite O, and then the last fella is A, adjacent. Okay, so if we're looking for the hypotenuse, we're going to use either sine, silly, old Harry, cos is cot, herring, tan, theta is trolling off America. Okay, so we are looking for H, so we can use sine or cos of those, okay? Sine or cos. So if we're going for cos, so if we're going for sine, it's going to be O over H. So sine of 20 O over H. Okay, so it's going to be sine, move it up, is equal to O over H. O is going to be, oh, wait a second. Oh, sorry, it's going to be cos, because opposite, okay? Sorry, that's the mistake. Cos theta is equal to A over H. So that will be O, and that will be A. There we go. So cos 70 is going to be equal to A over H. Is going to be equal to 686 divided by H. Okay, so H times cos 70 is equal to 686. Okay, so H is equal to 686 over cos 70. What that basically is going to be is right, I'll flick that around. Sorry, I have it all mixed up now in this drawing. It's going to be 686 cos 70. So 686 cos 70. Yeah, and type in the calculator, we're going to get 234.63 newtons. Okay, so it's 234.63 newtons. Okay, so that's that component. The parallel component is 234.63 newtons. Okay, now next part of the question states, what is the force of friction acting on the skateboarder on the ramp? So the force of friction acting on the skateboarder while he's on the ramp. Now I'm just going to check, make sure there's no questions come in. No, all good. So the force of friction acting on the skateboarder on the ramp, that's the next part we're looking for. The friction is what's going to try and slow him down. Okay, friction is basically what the ramp is going to, or gravity, what the ramp is going to do to slow him down. So we know that he is moving forward. We know the acceleration. So the force of friction acting on the skateboarder on the ramp is what we're looking for this time. So I'm going to say the force of friction from the ramp. Yes, I'm going to say FR. Sorry, the connection issue there. So the force of friction on the ramp is going to be, well, his weight is going to be acting against it, 234.63 in the parallel direction, worked out in the last question, minus, let's say, m by a, okay, his mass times acceleration. So 234.63 minus his mass, which was 70. The acceleration works out in the first question, which was going to be 2.977. Okay, 2.977. That's going to give you, you take them away. I get 234.63 minus 208.38. That gives you 26.25 newtons. Yeah. The force of friction from the ramp is just 26.25 newtons. Okay. Now, the next question, that is the long question. It says skateboarder maintains a speed of 10.5 meters per second until he enters a circle ramp such as by the end of radius 10. What is the initial centripetal force acting on him? Okay. So we go up the ramp. What is the centripetal force acting on? So the centripetal force is the force acting towards the center that keeps him moving on that radius or on that circle. So our formula for centripetal force is F equal to mv squared over r. Okay. So his mass is 70. His velocity, we're told in the question, is 10.5. Has to be squared. And the radius of the ramp is 10. 70 times 10.5 to be squared over 10. Gives you a value of 771.75 newtons. That is your centripetal force. Okay, FC in one call it. Very simple. Next part, what is the maximum height that the skateboard can reach? So the skateboard goes up the circular ramp and up into the air. What is the maximum height that it will reach? There's a few ways you could do this. Probably the easiest way would be to use your linear motion equations again. So V to U plus AT B squared is equal to U squared plus 2AS. S is equal to UT plus 1/2 AT squared. Okay. So one of them will probably work here. So U, if he's going, let's say if he's going up this ramp and up into the air, okay, he's going this way. So what we're going to say is his final speed, the maximum height is going to be his final speed. Okay. So at his maximum height, he's going to be still for a second before he comes back down. So his final speed is going to be 0. His initial speed, we're told in the question, is 10.5. His acceleration is minus 9.8, okay? If he's going up away from the ground, he's at a negative acceleration. And S, his displacement, is what we're looking for. Okay, so we have three choices. 1, 2, 3, 4. Looking for S, have V, we have U, we have A. We have V, U, and A. We're not looking for T. We have V, U, and A. We're looking for S. This is our guy. V squared is equal to U squared. Let's do S. V is 0 to V squared. U is 10.5 to V squared. Plus 2 times A is minus 9.8. S is just S. We're not sure. Okay, calculator out. I'm going to jig this around. So 2 by 9.8. So 110.25 plus it's going to be minus 19.6 times S. Equals 0 squared. So move everything around, get S on its own. We're going to have 110.25. It's going to be negative all over minus 19.6 is going to be equal to S. S is going to be equal to 5.625 meters. Okay, 5.625 meters is the answer. That is all that question done. So that is 2009 question 6. That isn't that easy a question, to be fair, okay? So that focuses a lot on the harder parts of mechanics, such as vectors and centripetal force and centripetal acceleration. So that's a good question to practice if you're not sure of the concepts and how to do it. Good question to look over, watch the video again and practice over and over. Right, we'll keep going. So the next question is based on similar concepts. Here. Okay, so this question is from let me get the year of this. (2012) question. Let's say it's part of question 12. 2012, not 13. Okay, part of question 12. So we get set up for this question. An Olympic hammer thrower swings a mass of 7.26 kgs at the end of a light, inextensible wire in a circle motion. Okay. Straight away, it's a clue it's going to be what circular motion is question. In the final complete swim, the hammer moves at a constant speed and takes 0.8 seconds to complete a circle of radius 2 meters. What is the angular velocity of the hammer during its final swing? Okay. So, angular velocity, we know is omega. I guess this is 1, this is 2012, question 12a. So omega is angular velocity. So as I do a lot of questions, I'm going to start off by listing all the things we do know. So we know the mass of the hammer was 7.26 kgs. we know that it moves at a constant speed, and we know it takes 0.8 seconds to complete one circle. So the period is 0.8 seconds. Okay, period means just the time it takes for it to go from point A all the way around the cycle and back to point A again. So all around the circle and back to A again, 0.8. We know the radius is 0.2. Oh, sorry, just 2. It's 2 meters. So that's most information we're given. So angular velocity is what we're asked on the first question. Angular velocity, why it's not equal to this yet, 2 pi over angular velocity. So the period is equal to 2 pi over angular velocity. We swap this around, we're going to get angular velocity is equal to 2 pi over t, okay? If we move it around, so we're going to have 2 pi over 0.8, 2 pi divided by 0.8, it's going to give you a value of 7.85, and we'll go to 4. Angular velocity is velocity, so it's rads usually per second. Okay. Next one. Even though the hammer was at a constant speed, it accelerates. Explain. Okay. So this goes back to the old velocity. So part 2. How can something move at a constant speed but accelerate? Well, so if this is our guy, he has a hammer in the Olympics, hammer throws like this, big heavyweight end of stick, and he's spinning it around in a circle like this. Okay, if he's doing this, even though it's at a constant speed, it is constantly changing direction. Okay, so even though something is going at a constant speed, because it is constantly changing direction, it's constantly going from north to south and to east and to west, it is actually accelerating, even though the speed doesn't change, because acceleration is defined as velocity divided by time. Okay, so velocity will change, change in velocity divided by time, and velocity is equal to speed plus direction. Okay, so if the direction changes or the speed changes, the velocity changes. Okay, so if the speed or the direction is changing, the velocity is changing too. So a change in the velocity would therefore create an acceleration. So if the direction is changing constantly, that means the velocity is changing. And a change in velocity will cause a change in acceleration. So it is always accelerating. Even though it's going around the circle at the same speed, it is still accelerating the whole time. New. Calculate the acceleration of the hammer during its final swing. Okay, so during its final swing. The first question we worked out, what was its angular momentum or angular velocity in the final swing? This time we're trying to find its acceleration in the final swing. So we knew we worked out already omega was equal to 7.854. Okay, that was our angular velocity. Acceleration, when you are dealing with angular velocity, can be worked out with acceleration is equal to angular velocity times the radius. Okay, so A is equal to 7.854 times v squared times the radius of 2. Seven 7.854 squared times 2. A is equal to 123.37. And because the acceleration is going to be meters per second, 2b squared. Okay. So it's quite straightforward. Multiply the accelerate or multiply the angular velocity by the radius. Okay. So the next question is calculate the kinetic energy of the hammer as it is released. Okay. So kinetic energy KE is equal to half mv squared. KE is half mv squared. KE is equal to half mass of the of our hammer was 7.26. Velocity of the hammer. Okay, we don't know the linear velocity. That's the problem. But we do know that linear velocity is equal to the angular velocity times the radius. Okay, so V is equal to 7. Where's it gone? 854 times 2. V is equal to 15.71. Now, a half mv squared, mass would be 7.26, V would be 15.713 squared. K is equal to half 7.26 times 15.712 squared. KE, kinetic energy, is going to be equal to 896 joules. Okay, not too bad. Oh. That's another question finished. We're going to do one more before we finish up. And I'm just going to find it now. It is based on simple harmonic motion. Okay, so I'll get this one done nice and quick. So simple harmonic motion, we're talking about pendulums, we're talking about springs. A simple pendulum can execute simple harmonic motion. Explain the underlying term. Okay. Simple harmonic motion, we say, is occurring. SHM is occurring. We say it's taking place when the acceleration of a body is proportional to the displacement. Simple. Okay, the acceleration is proportional to displacement. When does a simple pendulum execute simple harmonic motion? Next part. So when does a simple pendulum execute simple harmonic motion? Well, the answer to this is when it's oscillating at a small angle. Usually they say an angle less than 5 degrees. So less than 5 degrees, okay? Usually. Now, that part might necessarily be needed, but this just in a small angle should be enough. What is the relationship between the period of a simple pendulum and the length of the simple pendulum? So the actual relationship is that the period squared is proportional to the length, okay? So if you look at your log tables, you find the formula, period squared is proportional to length, or you could also say the period proportional to root the length. So as the period square gets bigger, so does the length. Okay. Now, next part. A stretching can execute simple harmonic motion. A spring has a natural length of 50 centimeters. A mass of 60 grams is hung from the spring and is allowed to oscillate with simple harmonic motion. Here is a period of oscillation of 0.85 seconds. Calculate the spring constant. Okay. So the spring constant can be calculated. Well, the spring constant is K, okay? So K is what we're looking for. We know, okay, we don't have any formulas of that, so W squared is equal to K over M. We have the mass, so this is probably the way we go about it. So first thing we need to find out is what is W? We're looking for K, we have W, we can get W, we can get M. What is K? So W can be found with T is equal to 2 pi over omega. Sorry, I shouldn't say W, omega. Omega is equal to 2 pi over. We're told the period of oscillation is 0.85 seconds. That gives us 7.39. That's for answer for omega. Now we're looking for K, don't forget, not omega. So omega squared is equal to K over M. Omega squared times M is equal to K. So 7.39 squared times M, which is 0.060, is equal to K. Multiply by 0.06. Answer for K is 3.28 Newton meter. Okay, Newton per meter. There you go. So that is the spring constant worked out. Okay, so that is the second last part of the question. The last part of the question simply says, find the length of the spring and the mass is at rest. So what we're going to use for this. We know F is equal to minus Ks. We know K is equal to 3.28. We know S okay, so F is equal to minus Ks. S is equal to, we're not sure. Okay. We know what K is. We don't know what F is. We don't know what S is. So F force, okay, is also equal to W, which is equal to mg. So mg is equal to minus Ks. So mass of this is 0.06. Gravity is 9.8. K is 3.28. S is S. Okay. So 0.06 times 9.8 is going to give you 0.588. That's equal to 3.28 S. You get S on its own. S is equal to 0.588 over 3.28. Work that out. Gives you 0.179. Okay, that's distance meters, or 0.18 meters. Okay, so that is S. So when the weight is put onto the spring, we add on an extra 0.8. The initial length was 0.5 when it was at rest, so 0.5 plus 0.18 gives you 0.568 meters. Okay, that's that question. So that's all for today's lesson. The video will be up online as usual, and we'll talk to you next week.